Okay, all right, you guys. So we're gonna end up emailing out two different videos. The video Corbin did will be on all the KSP stuff we've gone over, and right now I'm gonna go over the titrations. Okay, so you can see why this review is scheduled for 2 hours because we're through half of the material, and yeah, we still have a whole titration to do, but this is a good review. He did a lot of great problems, and Corbin wrote all those problems by himself. Like, he didn't look stuff up, he made them all up, and so, yeah, give him a hand. It was valid. Okay. But, as we were sitting here, we remembered something that we didn't incorporate into our actual review on the boards, so I'm going to erase something, we're going to talk about it right now. And that is, how does the auto-ionization of water affect pH? Right? Oh, I know, I hear like everyone, oh. But that is something that for some reason he kind of loves. So let's just do it, okay? All right, it's not too difficult. It follows a pattern. And we wanted to incorporate it. Okay, so with acid-base chemistry, number one, you guys should be able to take a strong acid, recognize the strong acid, and get the pH of the solution. Also, if you are given a weak acid and Ka values, get the pH of the solution. So there is a situation, right, where it's not that cookie cutter, and that is when you add acid, right, that produces H+, and H+ concentration that is extremely small, right, especially when we do a strong acid. That's usually the example we've seen. And so when you have an H+ concentration coming from a strong acid that's extremely small, if we try to take the pH of that, like for instance, let's say we have HCl, our favorite strong acid we always use, and if I added 1 times 10 to the -8 molar of HCl, because it's a strong acid, I know it's 100% dissociation. I also know that the H+ concentration that this would produce is the same number, 1 times 10 to the -8. If I take the negative log of that to go straight for my pH, right, I should get a pH of 8, right? But that doesn't even make sense, because how do I put a little bit of acid in water? Water's at 7. We know that it should go just a little bit acidic, right? So how does it go to 8 basic? The truth is, it doesn't. So this is where we have to factor in the auto-ionization of water. Okay, so let's describe what's happening, and we'll bust into the titration. So in a solution before acid is added, there is water, and it's auto-ionizing with itself, or it's reacting with itself. And that equation looks like H2O plus H2O gives me H3O plus OH minus. Okay, so that makes sense, right? We've seen this before, auto-ionization of water. We have a K constant for that. It's the Kw, 1 times 10 to the -14, which is something you absolutely need to have memorized, because that value helps you go between Kas and Kbs of other weak acids and weak bases. But when we look at this, what's happening is one of these waters ditches its hydrogen to the other, and one loses out on one. So you get the H3O and the OH minus. This is an extremely important thing to understand, the next thing I'm about to say. So make sure this gets written down or this makes sense to you. The H3O, or the hydronium concentration that comes from water, and the OH minus concentration that comes from water will always equal one another, right? You can't get 10 of these that come from water and 5 of those, right? It wouldn't even make sense. Let's try to figure out, why does that not make sense? Because in the reaction, one water takes the other and will always result in one or the other, right? They come in pairs from water, specifically, right? So, if we go back to this situation, what we have is we have our Kw of water, right, is equal to the concentration of my H plus times the concentration of OH minus, right? If it's just water, we know these two numbers are the same, or 1 times 10 to the -7, right? But if I add a little bit of acid to water, this is how I'm going to go through it. I'm not going to go through an ice table or anything like that. This is what I'm going to do. I know that my Kw will still be equal to my H plus concentration total. So the H plus that comes from water and the H plus I added from my acid times the OH minus concentration. So if I rewrite this now, my Kw, which I know that number, is equal to my H plus concentration, which is 1 times 10 to the -8. That comes from the acid. And I'm going to add an amount I don't know, X, that comes from water. I don't know that amount. And I'm going to multiply by my OH minus concentration in water, which would also just be X, because the amount of H plus that comes from water is equal to the amount of OH minus that comes from water. So this is just X as well. So I know what the KW is, so I'm going to switch this out for a real value. So what you do in this circumstance is you solve for the X value, right? So you're going to FOIL this out, put this on the other side. It's a quadratic, okay? And since we didn't prepare for this part, but it was important, I don't have the number, okay? But you solve for the X, right? And you've been doing this a lot. Once you get the X, all you're going to do is now find the total of that box. Whatever your X value came out to be, plus the amount of H plus that comes from the acid. That will tell you your total H plus in that solution, okay? And so if you take the negative log of that, you would probably get something like 6.94. So just a little bit acidic, and it would start to make sense. Yeah, that does make sense. It would just go a little bit acidic. So why is it that we don't ever worry about this, and we haven't really worried about this with other acid and base problems? Well, if we think about Le Chatelier's principle, when I add enough acid, it ramps up this side of this equation, right? Because this is just for water with itself, but all of a sudden, a bunch of these are coming from another source. So if I ramp up this side, we know it shifts back this way. So water stops doing that with itself when I get enough acid in there. So most of the problems we deal with result in this situation where water stops autoionizing with itself in a way that will affect the pH. But when it's a very small amount of acid, this still comes into play, and this is the way you do it, okay? All right, so you can go back and watch that again. We thought that would be an important one to go over just in case that gets brought up. Let's see the part slide over. Okay, so now what we're going to do, we're going to get into the titration, okay? Now, titrations, I don't know why, but they seem scary. They feel scary. They're big, long problems, and they're worth a lot of points. They've been smoking people on SmartWorks. I keep getting texts and calls late at night like, oh my gosh, like, this thing is killing me. Or I'm not kidding. I've had a lot of calls that have been like, I can't do a single problem. And I get that. Titrations take a lot of steps. It's not something you're going to get right off the bat. But I want to reassure you, titrations are a pattern, and the pattern never changes. So that's why, if anything, a titration problem is probably one of the most crucial problems for you to do several times. Because it's just a pattern. It's one of those problems where if you just knew how to solve it, but didn't really know why you were doing that, you could get all of the right answers, right? Because it just follows the same pattern over and over and over again, okay? So I want to make sure you have that pattern. That's what my focus today is going to be on. Showing you at which point in a titration do you do what pattern. And how do you know where you're at in a titration? How do you know how to begin the titration, right? Hopefully by the end of this, next 45 minutes, that's super clear. And then you can watch the video again and make sure you do plenty of problems. So all titrations follow the same patterns. And that is, I'm usually given a weak acid or a weak base to start with. And then I'm going to add a titrant, which would be a strong acid or a strong base, just whatever is opposite from what I originally started with. And so I noticed that one of the things, most of the problems you've done are on SmartWork, it gives you a weak acid and you titrate it with a strong base. But in this one that I have on the board, we have a weak base and we're titrating it with a strong acid. It doesn't matter, the pattern doesn't change depending on which direction we're looking at it. Okay? So they all are something like this. If I calculate the pH for the following situations, right? I have 0.01 molar of a strong acid is added to a 100 milliliter solution of 0.015 molar NH3, okay, which I immediately recognize as a weak base. So already in this problem, it was important that you had who was your strong bases and who were your strong acids memorized. If you don't have that, and I've just been sort of skating by, I picked some obvious ones, but if there's something you don't recognize, then it's a weak something, right? And if it's something you recognize, it's a strong something usually, right? So go off of that and make sure you know. So I know this is a weak base. I've given you the KB. So I want you to get a pH. We're going to go for a pH at 4 different spots. A pH before any of the HCl was added. A pH when I add 75 milliliters of the HCl, when I add 150, and when I add 200. This is a very familiar problem. They're always like this. But I'm going to highlight one thing before we start in this part right here. Before any HCl was added, I think when it's written like this, it's pretty simple. You know what to do. I'm like, oh, I'm going to take how much weak base I have, throw it in a nice table like I've been doing. But for some reason today, problem number 5 on the example worksheet was killing a lot of people, and it was literally just this. It was just this line right here. Just a simple ice table with Cn minus. Now I bring that up to highlight the fact that they all follow these same patterns, but they hide behind a wording that can be difficult to decipher. So that will be the hardest thing for you on the exam, I'm sure. But it's something that's difficult for Corbin and I to replicate. But I bring it up because I want you to be confident in the ways you already know how to solve anything with acids and bases, because it will be one of those. But it's up to you to decipher what to do, okay? So to begin this, I would want to start off with the pH before any HCl was added. So let's look at this as if it was a titration curve. My y-axis here is going to be pH, and my x-axis here is going to be liters of HCl. If I'm starting off with a weak base, I know that my titration point to begin with will be towards the top or above pH 7. But will it be clear up here around pH 14? No, because that's the land of strong bases, and we're dealing with a weak, okay? So we're going to be somewhere here. If you're asked to pick a pH titration curve for a situation like this, and you see a bunch of them that start at 14, you know that those are wrong, right? That doesn't make sense, because this does not give me a pH of 14. It will give me something probably around 10. So I'm going to be right here, and I'm going to start. We know that as I keep adding some of this acid, we know it'll come down until all of a sudden I get the dip, and then I approach the pH of the acid. And this acid is a strong acid, so it will approach close to 0? Yes. This one will go down low. Okay? So there are a couple positions on a titration that are extremely important, right? There is this entire section right here, before equivalence point. And anything before equivalence point has a specific way to solve it, and it will always be that way. Whether it's this thing in total reverse, whether I had a weak acid and a strong base, it doesn't matter. The situation is the same before equivalence point. Then there is equivalence point. That is another type of road to take. It's a different way to solve, right? So there's ultimately going to be 3. Before equivalence point, at equivalence point, and after. And they'll all follow the 3 patterns, depending on which situation you have. So the very first thing that I do, that Corbin does, that Taylor does, that anybody who I knew that could rip titrations does, the very first thing is do C1V1 equals C2V2 for their titration. The reason you do that is because before I even start with any of this, if I take my situation and do C1V1 equals C2V2, I can immediately solve for the volume amount of HCl that is my equivalence point. And that's crucial, because the moment you know that point, then you go to the 3 points they want to know. And you can highlight, probably one of them is the equivalence point, and you can mark the ones that are before and the one that is after. And you immediately know how to solve those points, because it follows the same pattern for that situation, okay? So if you do C1V1 equals C2V2, so concentration of the one, volume of one, concentration of the second, volume of the second. So we would have concentration of the base, or 0.015. I know this is small for you in the back that can't see, but you guys have done this plenty. Times 0.1 is equal to my 0.01 times my x. I don't know what my equivalence point is for my acid. When I solve for that x, you'll see that it's this one. 0.15 liters, or 150 milliliters, in this titration is the equivalence point. Remember, that is the first thing you do every time, because now we immediately know so much about this. I know that at 150 milliliters, it's right there. I also know that to solve this, I'm going to do the Henderson-Hasselbalch equation. I immediately know that, so it's going to be easy, because it's before equivalence point. And before equivalence point, that's the equation you use every time. Does it ever change from that? No, it's that every time. So you can be really confident about that. And then I know at this one, I'm at equivalence point, so I know what I'm going to do. And after, I also know what I'm going to do. So we're going to walk through this. Now, I'm going to skip one thing. And so you got to let me skip one thing. That is this one. You can do this one on your own. I'm not concerned about this one. We've done tons of these. This is just a nice table with what I have and the KB, right? So this one comes out to be like 10 point something. Let me see. I don't know if I even wrote that one down. Yeah, you guys, 10.7. 10.7. Okay? The pH beforehand is 10.7. You go back in the video. I want you can do this one on your own. Get to there. Okay? Let's jump into the titration when I actually start adding things. So, first part. Okay, the first BAA table, right? Now, to make this really clear again, the first step was C1V1. But once that's been done, how do you start any position on a titration? Meaning, how do you begin before equivalence point? How do you begin at equivalence point? And how do you begin after? A BAA table, every time. A BAA table can help describe exactly what is happening to you. So in a BAA table, I want to write my reaction up top. So the reaction that I have is ammonia, and I'm adding my acid, right? So is it okay for me to just go H plus here, or do I need to put HCl? H plus is absolutely fine. Why don't I have to put HCl? Because I've seen a lot of people kind of just, well, the only thing that confuses them is, what's the equation that I write? Just so you know, in a titration, I'm just looking at acids and bases. So any of those conjugates, like a Cl minus, that's a spectator ion, or an Na plus, or something like that, just discard them immediately and just look at what's important. So I like to do it like this, just to keep it really simple and not have to keep track of conjugates and things that aren't participating. So NH3 plus this is going to give me NH4. Okay, for me, that's plenty, right? That's all I needed to solve this problem. So, do I have some before here? Absolutely, right? What is the before? Do I do the concentration of NH3 that I was given? It's a BAA table, you've done this, so you know no, right? I do it in moles. Because in a titration, the ultimate factor, the thing that I'm really trying to do is take a number of acid or base molecules. In our situation, I have a number of base molecules. And I'm going to add a certain number of acid molecules to try to cancel those out. Concentrations don't help me do that. Because I could say something like this. I have a 0.001 molar concentration. It sounds pretty small. But if that solution is the size of the Great Lakes, it's a ton of molecules, right? So a concentration doesn't tell me really anything. It gives me just a ratio. But if I knew that I had 5 molecules of base, I want 5 molecules of acid to titrate it, right? A 5 molar solution of base and a 5 molar solution of acid can result in completely different numbers of actual molecules, right? So BAA tables are done in moles, okay? So when I do the moles out here, my original is 0015 for this, okay? Now, the H plus, I'm going to look at how much I added. So I do that, and this is going to be the 75 milliliter mark. This is the beforehand, the first step. And I'm going to get 7.5 times 10 to the negative 4. So that's how much I'm adding. So in this situation, I obviously have, I'm before equivalence points, I'm going to have more base than I'm adding acid. So in this situation, I'm going to have base left over that went unreacted, and all of the acid will react. So down here, this is going to be 0, because this is a smaller number. Every one of these is going to get a chance to react with one of those. But some of these would be left over without having a chance. So when I take the difference between these two, that'll tell me how much of the base did not react, right? So as I do that, I get 7.5 times 10 to the negative 4. So how do I know how much NH4 is there? Well, I know how much because I can only produce as much product as my limiting reactant, right? Or the thing that I have the least amount of. And over here, my smallest number to begin with is this one right here. So I can only produce as much NH4 plus as my smallest number. So I'm going to pull this number down for how much it produced of this as well. Are you guys with me on that? Yes. So here I am at the bottom of my BAA table. The only thing that's left over is my original weak base and its conjugate acid. So before equivalence point, the situation will always look like this. These two pieces, and this one is 0. The titrant is 0, always before equivalence point. These two pieces, and this one is 0. And when you see that situation, at any time, you're going to do the Henderson-Hasselbalch equation, right? Every time to get what the pH is or the POH. So, what is the Henderson-Hasselbalch equation? Well, it says that the pH is equal to the pKa plus the log of the conjugate base over the acid. But we are dealing with a base, so everything in that equation gets flipped, right? So instead of a pH being equal to a pKa and all that, this is going to be a POH, because I have a base, is equal to a pKb plus the log of all of those things, right? So I have my POH will be equal to my pKb, and in this case it's 4.75, I believe. Yep. Plus the log of my acid amount, which is here, 7.5 e to the negative 4 over 7.5 e to the negative 4. What do you notice with that? It's 1. Those two numbers are the same, right? So when I do this out, I get the log of 1, which is 0. So this whole piece didn't actually do anything for me. And my POH is equal to my pKb, right? So I'm highlighting a situation that's before equivalence point that also has another name called half equivalence point. And half equivalence point is when I have equal amount of moles of the base and its conjugate acid. Equal amounts at equilibrium. Or, to switch it, if I had equal amounts of moles of my weak acid and its conjugate base, right? As long as there's equal amounts of moles of those two, that is half equivalence point. And in that situation, your POH, or your pH, is equal to the pKb, or the negative log of the Ka for that species. Always, okay? So, if we went back to the top here, because we did C1V1 at the first, and we were able to solve for the fact that 150 milliliters of adding HCl was equivalence point, you could have looked at 75 milliliters and know that's half of what my equivalence point is, so that is half equivalence point, and not have done any of this, and just take the negative log of the Kv of that, and you were done for that spot, right? So there are a couple shortcuts. That is one of them, right? And they like that one because it's for students who understand that, they're quicker through, but students who haven't seen that, you can still just do it completely out. You'll just end at that same thing, okay? Did you guys see that? Do you see that point there? Okay, it will always follow that pattern for before equivalence point. So if I get a POH that's equal to this, what is my pH equal to? 14 minus this, right? So in this situation, my pH is equal to 9.2 something something, right? Right there. Does that make sense that it should be in the 9s for pH? Yes, I should be basic still. Because I only had base left over, none of the strong acid was left over. It should still be in the basic region. Okay? Alright, so let's move on to the next situation. The next situation is equivalence point. So when I've added the same amount of moles of the weak base and the strong acid. So in this number here, so again, NH3 plus H plus, NH4 plus. Okay, so if I know my initial here, if this is equivalence point, this number has to be the same as that one, right? So they equal each other. So that means when these two react, all of these will get a chance to react with all of these. In fact, we're perfect here. So we get 0 and 0. And how much of our conjugate acid is left over? That same amount, because I look at who my limiting reactant is over here to produce how much is this. I try to pick the smaller number, they're the same. So it will produce that same amount. Yeah, what's your question?
Just for terminology, say like before there's one kind of called the buffer region, right?
Yeah, it's called the buffer region. Yep. Good. Okay. So, in this situation, at equivalence point, it will always look like this for your BAA table. These three numbers will be the exact same every time. Every time. And you will get 0 for this and 0 for this. All reactants have been used. And that should make sense because equivalence point was when if I had 5 molecules of the base, I wanted to add 5 molecules of the acid. And when those two came together, right, there's nothing left over. I don't have a situation where maybe it was 4 and 5, and so I had a thumb or one of them left over, right? It is zeroed out, okay? So one of the things I've noticed that's difficult for students is they get to this point, I think you guys are actually pretty good at BAA tables, but then they stall out right here. And they go, okay, what's the pH now? How do I get that? Because I can't use the Henderson, and that's a beautiful equation that everybody sees that, a situation where they can use that, and they love that because it's easy. This is still easy, but we have to answer a couple questions. Look at what's left over. Who is the only piece still on the table that could affect a solution's pH? Just the conjugate. Is it an acid or a base? It's an acid, right? So should you expect the pH of this solution at equivalence point to be acidic or basic? Acidic, right? So that's the reason why when you add a strong something as your titrant to a weak something, the pH at equivalence point will be towards the side of the titrant, right? The titrant in our case is an acid. It's HCl. So at equivalence point, our pH should be below 7 or towards HCl for this particular reason right here. The fact that conjugate acid is the only thing left over. So in order to now solve for what the pH is, this is all in moles again, right? I'm going to do the classic Rice table, right? But this is in moles, so in order to do a Rice table, I have to divide this and get it into a concentration or molarity. So the only way I can do that is to divide now by the total volume of my solution I've created. So what is the solution you've created? Well, at equivalence point, we know we've always had 100 milliliters of base to start with. And I added another 150 of my HCl. So my total is 250 milliliters. So I take this and divide it by 0.250, right, per liters to get what my concentration is. And you should get 0.006 molar. Okay, so now I have it in molarity. I can plug it into an ice table. So I come over here. My new equation now does not deal with these anymore. These are all gone. It's only this. So what does this do in water? NH4 plus H2O is going to end up giving me an H3O concentration plus the base of it. Are you guys okay with me getting that equation? Are you guys good with transferring that over? Okay, good. So I start off with 0.006 moles of that. Minus X, 0.006 minus X. You guys are good at this. Water, so it doesn't count. 0, 0, plus X, X, and X. Okay? So now, in my equilibrium expression for this, I'm going to get this situation. X squared over 0.006 minus X is equal to what? A Ka. So another big mistake is dropping down that Kb that was given to you in the problem. But that is specific to ammonia. We have ammonium. So we're going to do the Ka. So remember, you take Kw is equal to Ka times Kb. So we can use Kw to switch us around. So the Ka for ammonium is 5.55 times 10 to the negative 10. Can you assume this to make it easy? Absolutely, right? These numbers are different by a factor more than 1,000. So I'm going to get rid of this bottom x here. And I take this and I multiply this up. And then I take the square root of that to get my x. So solving for your x in this situation, you should get, let's see if I do it out. Yeah. X is equal to 1.82 times 10 to the negative 6. So if I know my x value, I now know what my H3O concentration is in that solution at equivalence point. And that's the only factor that is a pH, right? So if I take the negative log of this number, then I'll get what my pH is. And my pH should come out to be, did anyone do it? 5.739, right? So pH at equivalence point is 5.739. Okay, so let's highlight some of the things we did here. At equivalence point, you get a BAA table that has all of these numbers like this the same. You take what your remainder is, which is only the conjugates, and you divide it by the total volume of your new solution. So it's crucial that you knew it was 150 or equivalence point amount plus the original amount, so 250 for us. And we got a concentration. And then we knew that was the only thing affecting the pH at this point. So we brought it into an ice table, right? So basically you're noticing one thing. If you are dealing with one species to affect a pH, you do an ice table, right? If you're dealing with two things, like a titration, and they're opposite, an acid and a base, you do a BAA table, right? But in the situation here, we only had one thing, so you had to go to an ice table. We do it absolutely normal, like you've seen. We just had to make sure we switch the KB given to the Ka, because this is now the conjugate, and we're able to get our X, which told us this, which is everything to us for this, right? And we were able to get the pH. And it makes sense that our pH is below 7, because we said, wow, at equivalence point, the only thing left over is an acid. So it should drop the pH a little bit, right? So far we've gone over those two areas. And in every titration, it follows that exact pattern. Before equivalence point, Henderson-Hasselbalch in a BAA table. At equivalence point, this situation, here's the only thing left over, and a Rice table to solve for the pH. Okay?
So on that number 5 problem today in class, you used the term endpoint. Is that the same as equivalence?
Yeah, so an endpoint, I'll explain that. So an endpoint is a chemistry term when they actually use a pH paper or some pH indicator to try to predict exactly where that equivalence point's at, right? So it's an equivalence point estimator. So when you hear something like, it's titrated to its equivalent point, to its endpoint, it's like, wait, are those the same or are they different? Yeah, endpoint kind of sounds like we mean like all the way blasting it with the titrant until it gets the pH of the titrant. No, it sounds like that, but that's not what it is. The endpoint is specifically when that pH indicator flips its color. And they try to make that so it's at the equivalence point. Oftentimes that's what it indicates.
What about when it gets to the half equivalence point?
So what do you mean by that? Half equivalence point was the situation we just did at 75 milliliters. Are you saying to get the pH, or what's the terminology here?
Okay, so I guess that would be your half equivalence point.
Your half equivalence point is the 75 one we did here. Exactly. And half equivalence point is when your pH is equal to your pKa every time. Every time. So if you know that's your half equivalence point because you did C1V1 equals C2V2, then you don't even have to do a BAA table. You just know your pH is equal to your pKa. Okay? All right. So let's finish this thing. We have a good chunk of time. This is great. So finishing this up, we have one more position. Now, are you guys comfortable with what we've done so far? Okay. It is this pattern. Now let's just do the third situation. The third situation is beyond equivalence point. So let's get a nice BAA table up here. Okay. So we'll rewrite our equation. We had ammonia plus the acid we're adding gave me this again. Okay, so we know this number before. We're getting good at this number. Okay, this was point, I think 0.02, or is it 0.2? 0.002. Thank you. Okay, 0.002, which means that my smaller number in this circumstance is my original weak base, right? I'm adding more acid than I need. I'm past that equivalence point. So I'm going to have some of this left over, but this is going to be 0. I'm not going to have any of that. So how much conjugate acid will be there if those are my two numbers? 0.0015, the limiting reagent, or the smaller number between the two. 0.0015. Okay, so how much of this is left over? Who knows?
5 times 10 to the negative 4.
It's 5, yeah, exactly. 5 times 10 to the negative 4. So I just took this, subtracted by that, see what's left over. So this situation is unique as well. This, you follow a different pattern. We're noticing that at each point in a titration, be it before, at, or after, this bottom row looks different. I either have just these two, or I have just this one, or I have just these two, right? And it's that pattern every time. So in this last situation, there's just these two. Now, to get the pH of this, there's a trick, and then there's like the long way. And you can do both. But usually the trick works, and the long way works every time. So kind of bet, I guess you just roll the dice on that, I guess. But I do the trick, because you know we roll the dice for all of these. But this is what we do. Understanding now what the pH is, let's go back to that graph. You see that graph that we made? We're to the right of the dot. Where does that curve go? It drops all the way down to the line. So I'm approaching the pH of the acid itself. So if I have a bunch of acid left over, according to my conceptual understanding of the graph, my pH should be approaching that of the acid I'm adding, and no longer really having anything to do with this. Now, there is some of this left over, but if I want to get the pH after equivalence point, I focus on the remainder of the strong. The pH will be right at that thing. And this hardly contributes. Now, I know that's difficult to see because you look at these two numbers and you say, well, this is a smaller number. I got 5 times 10 to the negative 4. This looks bigger, like this looks like it's more of an acid, like I got more going on here. But what I got to understand is this is not a strong acid. This is just the amount of weak acid I have, and I got to put that through a whole ice table, and it might spit me out just the smallest little amount of H+, right? But I have all of this here that is like valid right there in my face, H+, ready to change pH. So if I just take this number now and divide it by the total volume of this part of the solution, which would be 200 of my acid plus the 100 of original, so 300. So divide it by 0.3 here, I should get, I think it's 0.0116, 0.0166. 0.00166 molar of H+. If I take the negative log of that value, I'm at my pH for this, right? And that should be something like 2.77, okay? But I wrote this ice table here so we could look at it. What if you didn't want to do that? What if you don't want to assume? You're too scared. You think it might affect it. This might affect it. What do? Well, just do an ice table for all of the pieces now. Also divide this by 0.3, right? And you'll get your 0.005. So come into your ice table and rewrite the equation. I know that I have NH4 here. Okay, and it's going to try to react with water. And that's going to give me H3O plus my NH3. I have an initial concentration of this at 0.005. I also have an initial concentration of this one, at 0.00166, right? And you're going to go, okay, plus X here, 0.00166 plus X, 0 plus X, X, 0.005 minus X. So in my expression, I get 0.00166 plus X times X divided by 0.005 minus X is all equal to the Ka of that. Okay, so it's a lot of work, but it's just a nice table. When you solve for your X here, do it through, solve for your X, tons of math, nasty stuff, you're just going to get a really, really small number. And so you then go to this box and take your really, really small number and add it to this number, which would be a lot larger. So this really, really small number you just solved for will barely increase this one. That's why assuming over here that this does nothing is pretty valid, actually. Because this little acid here doesn't contribute very much. So after equivalence point, it's pretty easy to get the pH. Just look at what your remainder is. Okay? You look at your remainder, divide by the total volume, and you take the pH. So go ahead, and then I'll continue.
Is that the case
With most equations, that is the case. I don't know, Corp, most.
Yeah.
Yeah, it's been that way for me almost the entire time, okay? So that is after equivalence point. So a couple things I've noticed with students. You guys actually do this process pretty well, but it is the littlest, dinkiest, simplest mistakes, and I still make them to this day, all the time. But what I hope you guys will do when you're doing your titration, be confident in this exact process, whether it's before you do it exactly like we did with the Henderson-Hasselbalch, or at equivalence point is exactly like we did where we took the remainder and did an ice table, or after, where all I do is take the remainder of the titrant. It follows that situation every time, and be confident and take it slow. Don't make the simple mistakes. Biggest mistakes are not switching back out of moles, right? And not getting it into molarity. Something simple or something like that, okay? What are your questions? Before you guys take off, let's talk about questions so everyone can hear we get on the video. Yeah?
So I feel like we do tons of practice with these calculations, but you said that 13 of the problems are conceptual, so how can we prepare for that?
So the conceptual problems, to me, are problems like understanding whether or not a salt will affect pH and how, right? And also being able to predict something like as simple as like which of the following is a strong acid, and then, I don't know, Corbin, what do you think for another conceptual problem with acid-base chemistry?
Definitions.
Definitions of Arrhenius, Bronsted-Lowry, and Lewis acid. Maybe you're given an equation and he says, which of the following, A, B, C, or D, is the Lewis acid in this case, right? Or also being able to describe, like, if they say something like, you're doing a titration and you notice that the pH is approaching the pH of your titrant. Which of the following positions are you probably at, right? Before, at, or after equivalence point. So the thing is with this section, it actually kind of runs in reverse. Knowing how to do the math actually helps you do the conceptual. Does that make sense? Okay, he had a question, I'll get to you. Yep.
The lecture about titrations, talked about you only have like 4 different graphs. Remember that?
Yeah, I do.
I don't really understand that.
Okay, so as you're leaving, just try to be courteous to everyone else. Just try to keep it down, or keep the noise level down so we can talk about this. So his question is, what if I'm given a bunch of titration graphs and I'm asked to pick the correct one for the situation I'm given? So let's do a situation. Is it cool if I erase this right here? Cool? All right. Okay, so here's a situation. All right, I have a weak acid, and I'm adding NaOH. I want a titration curve as I start with this and keep adding some of this. So if I had 3 options, here are some. Okay, so we don't even need to label anything. Let's just look at what it looks like. I know without actually doing units, you could always argue like, well, we don't know what the units are. But if they were all drawn to scale at the same unit, that's kind of the point. I think when he did that problem in class, he like realized he didn't actually draw the units. You could make the argument like, we don't actually know that that's not it because we don't know like what the intervals are. But in this case, just keep it simple on this. If I have a weak acid, where does my titration start? Starts lower, below 7. So I already know I'm looking at this one or this one, and not the 2 outer. So these are done. So between these 2, how do I know which one is valid? Well, they all kind of go to the top here because this is a strong base, so they all are reaching almost to the top. But the difference is this one starts higher up than this one, right? And I have a weak acid, so it has to be this one. This is my titration curve, because if I had a strong acid, I'd start lower. This stuff like that simple. Yeah.
Is that like the only indicator you would say?
Yeah, this was the specific indicator right there.
Around the pH.
Yeah, where it started. Okay, and yeah, your question.
Here's the equation. It's like pH is equal to pKb.
Yep.
Is it a log of an acid?
It's the log of an acid over a base. So I'll say this really quick for everyone. In the Henderson-Hasselbalch equation, if you have a base, right, like our situation, it is the POH is equal to the PKB, and in the log part, it is always whatever goes on the denominator is the thing your Henderson-Hasselbalch is referring to, the PKB. Whose KB is that? That goes on the bottom, right? Holds it down at the bottom. So if it's a pKa in your Henderson-Hasselbalch, the acid's on the bottom, right? Well, everything on the bottom is being referred to by the K or KB values, exactly. It's a good point to not mix those up.
What are some situations where you need to take the inverse of the KB or the Ka?
The situation where you need to take the inverse of the KB or the Ka, do you mean inverse through Kw or inverse in terms of equilibrium?
I'm not sure. I just remember sometimes, like once we get to concentration, we need to take the inverse.
At equivalence point, I think I know what you mean. At equivalence point is when you gotta flip the Kb or Ka value you were given because you're now looking at how the conjugate alone affects the pH. So you will flip, most likely, the Kb or Ka value that they give you.
And that's when you're just looking at the conjugate of the acid.
Yeah. Okay, we are done. And if you have questions, we'll stick around for a few minutes.
Yeah.